Solving exponential equations by finding a common base. All right, before we can talk about the particular technique that is finding a common base, we need to talk about solving exponential equations in general. There's going to be two different videos on solving exponential equations because there are, in general, two different techniques to solve an exponential equation. One of them is finding a common base, and the other one is using logarithms, typically natural logarithms. I will reference this particular slide or piece of the worksheet in the next video as well. It's relevant to both. So, solving exponential equations. Here are some important facts. Unlike logarithms, we do not need to check our answers in the original equation the way we do with logarithmic equations, because exponential equations don't have any domain restrictions. So there's not going to be an answer that we get that doesn't work in the domain. So we're good. Wonderful. Another thing is that we can take the log of both sides of an equation. So if we have something like m is equal to n, then we can apply log base b, whatever base we want, to both sides of the equation. This might not sound super exciting. It might sound like the opposite of what we were doing in the previous problem, in the previous with the logarithmic equations, because we were trying to go the opposite way from here to here. But this is really important, and it does have a lot of relevance. Another thing, this is important. This is from a while ago. We did reference it in a video recently, but this fact that log base b of b raised to the x is equal to x is an important one. In particular, I'll do it in purple. This works with log base, let's do 3 to begin with. Log base 3 of 3 raised to the x is x. That's cool. But you know what's also true? Log of 10 log of 10 raised to the x is equal to x. Why is that? Because just a regular log is log base 10. Right? Log without any number written as the base is a base 10 logarithm. That is an assumption we make. Another thing, ln of e to the x is equal to x. The reason for that one is because that's the same thing as log base e of e raised to the x. Okay. I really want you to internalize this one. All right, this one right here, internalize it. Internalize it, and let me write it really big. ln of e to the whatever is the whatever. Pretty cool, pretty fun, pretty exciting. Not always relevant, but when it is relevant, it's very relevant. Final thing we need to know about exponential equations is that if you have two bases equal to one another and they have exponents, same base, different exponents, or the same exponent, who cares? It shouldn't be the same. But the bases are the same. We can take the exponents and set them equal to one another. Yeah. This is kind of like the equivalent rule as this one that we used in the logarithm video. And it's in fact this rule number 4 that we're going to be using to solve problems by finding a common base. If you have a common base, then set exponents equal to one another. All right. So solving exponential equations by finding a common base. Some numbers share a common base. So for instance, all of these numbers here, 2, 4, 8, 16, 32, 64, these are all powers of 2. The thing that all of these numbers share is that all of these numbers are powers of 2. They share a common base. 64 shares a common base with 16 because both of them are powers of 2. So also both powers of 4, but regardless, they have a common base. 16 and 64 have a common base. Right here. 3, 9, 27, 81, 243, all of those numbers have a common base. Those are all powers of 3. Right? You can see where this is going, right? 4, 16, 64, 256, these are all powers of 4. That's the relationship that these share with one another. 5, 25, 125, all powers of 5. And I don't know what color, orange. 6, 36, 216, these are all powers of 6. There are, of course, other powers than these. These are just the really common ones that we deal with. So if I'm looking at some examples of problems that we can solve by finding a common base, these are some examples. You can't find a common base always. There's only certain situations where you can do so. But if I look here, there's 2 ways I can look at this one. I could say that they're both that 9 and 81 are both powers of 9. They're also both powers of 3. They share a common base. So I could rewrite this knowing that 9 is 3 squared, 81 is 3 raised to the 4th power. That's what we have right here. Right? 9 and 81 are in the same family here. So if I replace 9 with 3 squared, I would get 3 squared raised to the 2x, right? 9 raised to the 2x is equal to, instead of 81, I could put in 3 raised to the 4th power, raised to the 2x plus 5. And we can use some rules, and we will, you'll see very soon, use some rules to simplify the exponents, and then we have the same base. Both of them will be base 3. 16 and 8. It might be tempting to say that they share 4 as a base, but 8 is not a power of 4. So we're looking at powers. They're both divisible by 4, but they are both not powers of 4. 16 is, 8 is not. But 16 and 8 are in the same 2 family. They're both powers of 2. So I could rewrite 16 as 2 to the 4th, and I could rewrite 8 as 2 cubed. And that would give us the same base. Here, 32 and 64, it helps to have this reference sheet, right? Because I can look through here. 32 and 64, those are also both powers of 2. 32 is 2 to the 5th, so I could have 2 to the 5th raised to the negative x minus 4. Right? 32 raised to the negative x minus 4. 64 is 2 to the 6th. It is equal to 2 to the 6th. So part of doing the common base thing is being able to recognize that families belong in that numbers belong in families together. If you can't recognize that, you'll have a harder time with these common bases, which is why I made this table. It took me a really long time to make that table. Not that that rant belongs in this video. Hey, you want a small off tangent? Because I know you're just sitting here doing math. Maybe you want a moment to like breathe. I learned that worksheets are a lot easier to make in PowerPoint. Take that information and do what you will, but if you ever need to make a worksheet someday for something, for some reason, PowerPoint. Use PowerPoint. Don't use Word. That was what I learned. All right, back to what we were here for. Let's do some problems. So we're going to solve some exponential equations by finding a common base. We're going to rewrite both sides with a common base. We're going to set the exponents equal to one another and solve the equation. We will not need to check our answers, though it's always a good idea. We don't need to. So I'm looking here. I see 25 and 125, and those are both powers of 5. 25 and 125 powers of 5. So I am rewriting 25 as 5 squared raised to the x minus 1. And 125 I am rewriting as 5 cubed. An exponent rule we have that maybe we haven't talked about in a while is the power of a power rule. So if you have x to the a being raised to the b, that's an exponent on the inside of a parenthesis, and then on the outside of a parenthesis, you can multiply those exponents together. So you have x raised to the a times b. So I will combine these together. This is 5 raised to the 2 times x minus 1. 5 raised to the 2 times x minus 1. Look at, we now have the same base on both sides, right? 5, 5, which means we can set the exponents equal to each other. All right, so that's all we'll do. We have 2 times x minus 1 equal to 3. If I distribute that 2 on the left-hand side, I get 2x minus 2 equal to 3. Adding 2 to both sides, I get 2x equals 5. Divide both sides by 2. X is equal to 5 halves. And here's the fun thing. We don't have to check our answer, but it's really not that hard to do so if we really want to, right? Plugging back into this guy up here is pretty fast, especially since there's only an x on one side. All we have to do, if we do want to check it, is do 25 raised to the 5 halves minus 1, plug it into our calculator, and see if we get 125. So I'm doing it right now. 25 raised to the 5 halves minus 1. I got 125. It's not a question mark anymore. Bam. Again, not strictly necessary, just, good idea every once in a while. All right, let's do another one here. Shouldn't have used the same base. Oh well, too bad. We're already here. Got 5, we got 25. These are both powers of 5. 5 is already written in the correct way. So we have 5 raised to the negative 6x. 25 is 5 squared raised to the 3 minus 2x. So I have 5 to the negative 6x is equal to 5 raised to the 2 times 3 minus 2x. I can set my exponents equal to one another because they have the same base. Both are base 5. So I have negative 6x is equal to 2 times 3 minus 2x. Distributing the 2, I get 6 minus 4x on the right side. Adding 4x to both sides, I get negative 2x equals 6. Dividing both sides by negative 2, I get x equal to negative 3. I do not have to check my answer. I can simply say it's correct. Though again, once again, like I did over here, it's not that hard to check it. So making a common base is one of these things that's just, it's convenient if you can do it. If you can't, then the method we'll talk about in the last video for this section will take care of our problems. Let's do two more problems. All right, we have 27 raised to the x plus 1 is equal to 81. These are both powers of 3. "27 is 3 cubed raised to the x plus 1. And 81 is going to be 3 raised to the 4th power. So we get 3 raised to the 3 times x plus 1 is equal to 3 to the 4th. The bases are the same. I will set the exponents equal. 3 times x plus 1 is equal to 4. Distributing the 3, 3x plus 3 equals 4. Subtract 3 on both sides. 3x is equal to 4 minus 3 is 1. Divide both sides by 3, we get x equal to 1/3. And there it is. Bam, done. Now this next one looks really scary, but I promise the only thing that makes it scary is that you have to factor a quadratic. So let's do it. Don't be scared. Don't be scared. It's going to be okay. Looking at 36 and 6, these are both powers of 6. So 36 I am going to rewrite as 6 squared raised to the 3 minus 7x. On this other side, we already have 6 as the base, and the exponent is x squared minus 4x plus 15. So I have 6 raised to the 2 times 3 minus 7x is equal to 6 raised to the x squared minus 4x plus 15. Both have base 6. We can set the exponents equal. 2 times 3 minus 7x is equal to x squared minus 4x plus 15. We're going to have to distribute everything on the left side and move all of it over to the right side, and then factor. Oh, here's the thing about me, guys, is that I chronically get my lefts and rights wrong. On the left side, you distribute, then move all terms to the right. Then refactor. And solve. So distribute. 6 minus 14x is equal to x squared minus 4x plus 15. All right, I'm going to leave my x squared over here, so I'm going to kind of, maybe I'll physically write it out. I don't want to confuse anyone. This is what I'm going to do. I'm moving this side over here before I'm even doing any math. I'm not even doing any algebra right now. I'm just going to rewrite this so that my x squared is on my left side. I like it that way. And then I'm subtracting 6 on both sides. So this will become 15 minus 6, which is 9. And then adding 14x on both sides. This is going to become 10. I guess it wouldn't hurt me to write that. I'll write it. Minus 6 plus 14x plus 14x. We get x squared plus 10x plus 9 equal to 0. This factors into x plus 9 times x plus 1 equal to 0. We get negative 9 as an answer. We get negative 1 as an answer. Those are both answers. Bam. Done. All right, so that's our first technique for solving exponential equations. Again, only works It only works if you have both sides in the same common base family. If they don't exist in the same common base family, let's say you had something like 11x equals 7 raised to the 2x plus 5, 11 and 7 are not in the same common base family of any number, you could not use this technique. You'll need the technique in the next video. So I will see you there in that video. Bye.